Notes on conservation of energy. So again, you want a notebook out for that. But before we do that, let's go ahead and talk about today's warm-up question. If you've got little side conversations, I'm going to ask y'all to bring those to an end so that you can all focus your attention up here, because we are going to get through quite a bit of material today, I hope, and then give you hopefully a fair amount of time. We'll see. It depends on how long it takes us, but hopefully a fair amount of time to work on or get started on the assignment 902.2 conservation of energy problem set, which will be due tomorrow. So let's talk about the warm-up. It says, two renters, A and B, move a TV into a new apartment building by different methods. If the TVs are the same size and have the same final position, who did more work on the TV and which TV has more gravitational potential energy? So we're going to assume that both of these TVs started at the ground and both of them are now all the way up on this fourth floor. Okay, so given that information, who does more work on the television? A or B?
They're equal.
They are equal. Okay, they are equal. And the same answer to the other one, more GPE equal. Okay, you would have an equal amount of gravitational potential energy as well, because if you have the same TV, which has the same mass, and you're bringing it to the same height, okay, that's obviously going to give you equal GPE, but that's also what you're doing whenever you're calculating work, is the force it takes to lift it up, that's going to be its weight, times the distance you lift it up. Because again, remember, it doesn't matter when you're walking forward. We talked about that in the work unit. If I just carry it across the floor, like this portion where he's just walking with it, that's not work. It's only work when your force is parallel to your displacement. Okay, and so in that case, it's perpendicular. So it's just the upward motion here that matters. And we talked about this with work, but we're going to now apply it to energy as well, because work is change in energy. So obviously, if we have the same work, we're going to have the same energy at the end if we started, of course, at the same place. And so both of those answers to the warm-up should be that they're equal. You have equal amount of work and an equal amount of gravitational potential energy. And these guys need to get new TVs, because those are those giant tube TVs that y'all probably have maybe seen whenever you were really young. I don't know. But nobody has these anymore. But anyway, please make sure that you have answered the warm-up question in Schoology. They are equal to each other. And one of the things we talked about with work, and this is what I was going to get to, last semester, is work is independent of the path taken. It doesn't matter if the TV goes straight up, or if it takes this zigzag path up the stairs, or if somebody found an even longer way to get it up there. It doesn't matter. Okay, your work is independent of the path taken. If you started and ended at the same point and you're lifting the same object upward, you're going to be doing the same amount of work. And that object will have the same amount of gravitational potential energy at the end of that. Okay, so again, make sure that you answered that. And if you want to jot something down in terms of notes related to what I just said, that might also be a good thing to have written down. All right, so at the end of class yesterday, we were talking about law of conservation of energy, just as a quick intro, and I showed you this video of Dr. Lewin with his pendulum, and he talked about the fact that the gravitational potential energy of this pendulum bob was converted into kinetic energy as it fell from the height where he released it. It got faster. And then that kinetic energy was converted back to gravitational potential energy again as it rose up to the other side, where it eventually stopped. And of course, it would keep doing this. Okay, and so energy begins as gravitational potential energy, transformed into kinetic, that's your energy of motion, and then back to gravitational potential energy again. But the whole idea is that the total amount of energy remains the same. The pendulum won't rise to a greater height than the height from which he dropped it, and he said that in the video as well. And it did pretty much rise right back up to where it started, and in a perfect world it would if we could get rid of air and friction and all of that stuff. Okay, and so we're going to assume those ideal conditions when we're talking about the law of conservation of energy, where we have no energy loss at all. So assuming no friction, how does the total mechanical energy of this pendulum compare at point A versus point C? What did we just say?
The same.
They should be the same. Okay, the total mechanical energy, and remember from our notes yesterday, your total mechanical energy is the sum of your kinetic and potential energy. So at point A, it's just potential, it's just gravitational potential. And at point C, it's just kinetic, that's the lowest point. So your total energy, it's changing the forms, but the total should remain the same. Okay, and that's what the law of conservation of energy states. So you could pick any point on here and talk about the energy forms present at any of them. I've got 5 labeled up there, but the total amount should be the same at each of those points. Now, how that amount is divided up between the different forms, that could be different, but the total should remain the same. Okay, and that's again due to the law of conservation of energy. So you could say that the mechanical energy at point A is equal to the mechanical energy at point C, and by the way, it's also equal to the mechanical energy at point B and D and E. Okay, pick a point. Okay, they should all remain equal if we're not having any energy loss due to friction or air resistance. Okay, because that total mechanical energy is constant, we can represent the energies with pie charts. You guys know pie charts from elementary school, but pie charts show parts of a whole. And so if the whole amount of energy is constant, we can show how the parts within that total are changing by showing different size pie pieces. And again, the forms of energy change as gravitational potential energy converts to kinetic energy and back again, but the total amount should stay constant. And so at point A, I could have a pie chart that's just gravitational potential energy. Okay, but at point B, my energy should be, since B is actually halfway between the highest point and the lowest point, it should be half and half. I should have half gravitational potential energy because I'm at half the height. Okay, and I should have the other half is at that point going to be kinetic. Okay, at point C, it's all going to be kinetic. That can't go any lower than this point. So if we use this as our baseline and we call it our height of 0 just arbitrarily, then we could say that it's all kinetic energy at that point. At point D, it's not quite back up to that halfway point between the heights. I have the heights marked with these dotted lines, so you can see C and E. And D is, of course, closer to C, so when I draw my pie pieces, I'm going to have more kinetic than I would gravitational potential, as opposed to this one that was half and half. And then, of course, when it gets all the way back up here again, where it stops moving for a moment before it turns around, that energy is all gravitational potential again. Okay, so you should be able to identify what the pie chart would look like at any given point if you know what you like where you started, kind of like this, where you could see you'd have more kinetic here or half and half, whatever. So you should be able to represent these or draw them on your own, or to identify things like that in a multiple choice type of question. Okay, but again, you're representing the different energy forms, and the pie chart should be at least mostly proportional to what you would expect it to look like. Okay, like this one, I wouldn't want to show like more gravitational potential than kinetic, for example, because it's obviously not closer to that end. If I had it up higher, I could do that. But we're not going to like measure and make sure you have the exact right percentage of your pie chart. Just make sure it looks reasonable. All right, let's see if we can use this same idea of the fact that we have this constant amount of energy to do some calculations. Again, these might be helpful for you to copy down onto your paper, but the question up there at the top says, if a 0.5 kilogram pendulum is dropped from rest at a height of 2 meters at point A, what is its gravitational potential energy? So at point A, we're going to figure out how much gravitational potential energy it has if it has this mass and this height. And of course, gravitational potential energy is going to be mass times gravity times height. On Earth, of course, we're going to use 9.8 as our gravitational acceleration. So we're going to take that mass 0.5, we're going to multiply it by 9.8 and then by 2. And when we do that, we get a gravitational potential energy of 9.8 joules, just because of the numbers that I used. Okay, and so my gravitational potential energy here is almost 10 joules, 9.8 joules. Okay, given that, what would my gravitational potential energy be at point E? 9.8. It'd be exactly the same. See, this is how the question's going to work. Okay, the question isn't going to do just what this says. It's going to say, if a 0.5 kilogram pendulum is dropped from rest at a height of 2 meters at point A, what is its GPE at point E? Okay, and you'd have to use that same thought process. Well, here it is at A. I know it's 9.8 here, and so it must be equal here because of conservation of energy. Or, how fast is it at point C? Same idea. Because you guys told me a minute ago that the total energy at A equals the total energy at C. So even though I didn't give you any information about kinetic energy, I can still answer this question. How fast is it moving at C? Well, I know that the total energy is 9.8 joules. And so it's going to be 9.8 joules down here. And so we're going to use that for our kinetic energy. Even though it doesn't tell us that we can, we can. Okay, you have to be able to do that on your own. Okay, this, by the way, is what makes this unit kind of difficult, is that just like last semester when we did work energy theorem, when you had to write out your own equations, same idea. You need to recognize that the gravitational potential energy at point A equals the kinetic energy at point C. And so if they give you information about point A, you can solve for point C. Okay, so let's go ahead and do that. So again, I have that 9.8 joules that I know is the total energy that I have, and I can set it equal to 1/2 mv squared, and I can solve for v because I already know the mass. Okay, so I have 9.8 equals 1/2 times 0.5, that's my mass, times v squared. Okay, and so if you get half of 0.5, that's obviously 0.25, and then I divided both sides by 0.25, and I have this 9.8 divided by 0.25 equals v squared. And so if I divide that, and then of course I got to take the square root, I get this, 6.26 meters per second. So even though I didn't tell you, hey, here's the kinetic energy at C, doesn't matter, you can still answer that question because you know what the energy is at A. Okay, so that's how you're going to be doing conservation of energy problems. Now this one I worked you through step by step. They're not going to be doing that on the test, okay, or even necessarily on all of your practice problems. Sometimes I will. Sometimes it'll say find this step, okay, now find this, okay, now find this, and that's a little easier because it guides you through the thought process, but you have to be able to get here on your own. All right, so let's go ahead and take a look at another one. A 0.5 kilogram pendulum is dropped from rest at a height of 2 meters at point A. So this is the same setup we started with last time. If it moves through point D at 5.8 meters per second, what is its height at point D? Okay, so again, this is what I told you we were going to do. Hey, here's some information about point A. Let me ask you about a different point. Okay, and so again, you need to recognize that you have to be able to write that energy transfer equation. Okay, so at point A, I have gravitational potential energy. What do I have at point D? Both. Okay, you can see it in my pie chart. Okay, so the total mechanical energy at A equals the total mechanical energy at D, and that's what that looks like. The gravitational potential energy of my pendulum at point A equals the gravitational potential energy of my pendulum at point D plus the kinetic energy at point D, because at point D there are two forms of energy. Okay, and so this is how we're going to set it up. All right, so from here, again, you'll notice I didn't give you anything about energy in this question. So I really don't want to leave my equation like that. I'm going to substitute in the variables. So instead of GPE, I'm going to substitute in MGH. And instead of KE, I'm going to substitute in 1/2 mv squared, because those are the variables that I have. Now, if the question said you have this much energy, I wouldn't need to do this step. Okay, but because it gave me heights and masses and velocities, I need to do this step. Okay, so now I have GPE at point A, MGH, equals GPE at point D, MGH, plus KE at point D, 1/2 mv squared. Okay, and I have a little subscript there to keep it straight. I have A and D labeled on there. Okay, and now we're going to put the numbers in. Okay, so at point A, I have my mass 0.5, gravity is 9.8, my height is 2. I already know what that answer is. We did it a minute ago. I could have just put 9.8 down there, okay, because we already did it. But I'm going to show you the steps. At point D, we have the same mass and the same gravitational acceleration, but I don't know the height, and that's the point, because that's what the question's asking for, so I still have the variable there for h. And then I know the velocity. It says it's moving at 5.8 meters per second at point D, so I have 1/2 plus 0.5 plus 5.8 squared. Okay, so from here, it's just algebra. The hardest part is writing the equation. If you can write that equation, you should be good. I mean, you might make a silly mistake, hopefully not, but The hardest part is writing the equation out. Okay, so let's go ahead and solve this one. That's 9.8 on the left, we already knew that. 4.9h plus, and all this mess right here, this 1/2 times 0.5 times 5.8 squared is 8.41. Okay, and so if I want to get that variable, that h by itself, and here's where some of y'all have problems. I say it's just algebra, but some of you guys try to add those two numbers together. You cannot do that. Just as a quick reminder, you cannot add 4.9h plus 8.41 together. Those are not like terms. Okay, so in order to isolate our variable, we need to subtract 8.41 from both sides. And then you'll have 9.8 minus 8.41 equals 4.9h, which is 1.39 equals 4.9h. From here, we just divide by 4.9, and we get our height of 0.284 meters, which makes sense. It's pretty low. It's almost all the way down to 0, but, oops, I didn't mean to click backwards. Okay, and comparing that from the height we started. Okay, so it's just barely above that lowest point. Questions about this calculation problem? I would strongly encourage you to have it written down as an example, okay, so that you can look back at it, because you're going to have problems like this today in your assignment. All right. So let's try another one. Okay, and instead of pie charts, I'm going to show you another way that we can represent our forms of energy. This one says, if a 75 kilogram man were to ride his sled from rest on a frictionless hill that is 22.3 meters high, how fast will he be traveling halfway down? Show the bar chart for halfway down. Okay, so we can use pie charts to show portions of energy, but we can just as easily use bar charts, okay, to show my energy forms before, my energy forms after. Okay, so initially this guy is at rest at the top of a hill. So what form of energy does he have initially? What does he have? If you're on top of a hill, gravitational potential energy. You're not moving. It says he's at rest. It's just gravitational potential energy. Now, I'm not going to worry about exactly what 4 blocks high means. I'm just going to make sure that if I draw something that's 4 blocks high on the left, that my total on the right is 4 blocks high. Okay, because I'm trying to show that I'm not gaining or losing energy because it says it's frictionless. So I want it to be equal. So at the end, and not really at the bottom of the hill, rather for halfway down, if he's halfway down the hill, what forms of energy should he have? Both gravitational and kinetic. There's no elastic here. Nothing's being stretched or compressed. So it's just those two. And it should be half and half because he's halfway down. If you have half the height, you will have half the GPE. Okay, so notice I still have 4 blocks. Make sure that you, if you're trying to answer a multiple choice question, make sure that you didn't like gain extra energy or lose energy from somewhere in a situation like this. If you want to show conservation of energy, your total mechanical energy needs to equal your final mechanical energy at the end. All right, so from this we can see how we can set up an equation. I can see that I could write my equation as GPE initially equals KE plus GPE final. Okay, and I could solve a question like this, how fast will he be traveling halfway down, with this formula. Again, you have to write the equation. That's what can make this tricky. Okay, you have to be able to do this. GPE initial equals KE final plus GPE final. And a bar chart is a tool that you could use to help you visualize those energy forms. So if you find it helpful to start with a bar chart, do it. Okay, but you might still see them in a multiple choice section. So just make sure you can at least interpret them. All right, so now we're going to look at this one. How fast will he be traveling at the bottom? Same scenario, same guy. So he still starts out with GPE. But if we're looking at how fast he travels at the bottom of the hill, okay, what form of energy would he have at the very bottom? Kinetic. Does he still have potential? No, not if he's at the bottom, not if he has 0 height. And so all of his gravitational potential should be equal to kinetic there, and this equation would look like this. Okay, now we didn't solve the last one, but you should be able to at least write the equation because that's your first step to solving it. My GPE initial equals my KE final. And could I solve it? Sure, I could figure out how fast he's moving at the bottom. In either case, okay, with either of those, either halfway down or at the very bottom. Okay, so let's go ahead and do that. Okay, we have our energy transfer equation. Our GPE initial equals our KE final. We're looking now at the one that asks how fast he's moving at the bottom of the hill. Okay, and we can substitute in, because I don't have energies, I have masses and heights, and I actually don't have the velocity, but I have these variables. So I'm going to set it up like this. My GPE initial, so mgh, equals my KE final, so 1/2 mv squared. And now I'm going to put the numbers in. The mass is 75, gravitational acceleration is 9.8, the height of the hill is 22.3. And that initial gravitational potential energy should be equal to his velocity, or his kinetic energy at the bottom, which means I can find his velocity. 1/2 times 75 times v squared. This entire left side is equal to 16,390.5 equals 37.5, that's half of 75 times v squared. From here, I would divide both sides by 37.5, okay, which is 437.08, but that's v squared, and then I would take the square root. And I would get that his velocity at the bottom is almost 21 meters per second, 20.9 meters per second. And again, I can solve that because I know that I have conservation of energy, because there's no external forces acting on the sky. There's no friction. Okay, I just have, looking at my man-Earth system, I just have gravitational potential energy equals kinetic energy. Okay, so here is his velocity at the bottom. Does anybody have a question about this one? No? Follow-up question. What conclusion might you make if you found out he is only traveling 16 meters per second? There you go. He already said it. What if you're not going 21 or 20.9? What if you're going slower? Probably friction, yeah. Okay, it said frictionless in the question, but what if I gave you a scenario where I told you how fast he's moving at the bottom, then you go, okay, well, there must be friction present. Okay, we talked about this last semester as well. We know friction can do work on a system, and that work, negative work, can remove energy from the system. This means that mechanical energy will not be conserved. If you have friction acting on your system, okay, or any external force acting on your system, then you're not going to have conservation of mechanical energy. Okay, you're going to have energy loss due to heat or sound or whatever, depending on what the force is. Okay, so again, if you have work being done, then you're not going to have equal amount of mechanical energy before and after, because work is going to be adding or removing mechanical energy from your system. Okay, bringing us to this. So, closed system versus open system. Okay, in a closed system, you can only have energy exchange within the system. This means there are no external forces or work, and your mechanical energy must be conserved. So this is the ideal conditions where we say, okay, we have no friction, we have no air resistance, we can use conservation of energy because there's nothing coming in, there's nothing going out. This is my closed blender, okay, as my analogy. Over here, though, open system, if you have an open system, which, by the way, don't turn a blender on without a lid, but if you have an open system, energy can be exchanged with the surroundings. Things can go in or out of your system. And that means that if you have an external force on your system, you will have a change in your mechanical energy. Okay, so you could have a situation where your mechanical energy is not necessarily conserved. It could be if you don't have an external force on your system. Okay, but mechanical energy could change in that type of system if you do have an external force acting on it, like friction or like air resistance or whatever that may be. Okay, so again, different types of systems. Again, in an open system, mechanical energy is often dissipated or lost from the system, so it is no longer available to do work. We talked about dissipated energy last semester. We're coming back to it. Okay, the sled loses mechanical energy due to friction generating heat. That energy still exists. Heat is still energy. It's thermal energy. It's just no longer useful. Okay, we can't use it to speed up or whatever, the case may be. Energy, total energy is always conserved if we think about not just our system but also the surroundings. The total amount of energy stays constant, but your total mechanical energy is not going to be conserved in your system if you do have an external force acting on it. Okay, like the sled slowing down due to friction. Okay, so let's answer this question. A 75-kilogram man rides a sled down a hill that is 22.3 meters high. At the bottom of the incline, he is still moving at a speed of 16 meters per second. how much energy was lost or dissipated due to friction. And I know that I lost some because he's supposed to be going 20.9 meters per second, and he's only going 16. So we would need to write out an equation. But I already know that mechanical energy is not conserved. His GPE at the top of the hill does not equal his kinetic energy at the end. You can check it though. Okay, his gravitational potential energy at the top, again MGH, is 16,390.5 joules. And I can look and see, is that equal to the kinetic energy at the end? Given that he's moving 16 meters per second, I already know the answer, but let's go ahead and see what we get. 1/2 of 75 times 16 squared is only 9,600 joules. So obviously, mechanical energy is not conserved. I have lost some. If I asked you how much did I lose, what do? I just have to subtract. Okay, I just have to subtract because clearly I started out with a little 16,400-ish, and now I only have 9,600. Figure out how much you lost, subtract. Okay, and so that would be equal to 6,790.5 joules. That would be how much energy was dissipated from the system, how much energy I lost, or it's also how much work was done by friction. We talked about that last semester as well. That work is your energy change. If you have an energy change, if you have dissipated energy, it's because friction did work. Specifically, negative 6,790.5 joules of work. And that's why we lost that. Are there any questions about this? Because this part's kind of a review from last semester. Okay. All right, guys, then I'm going to have you begin your MyOpen Math assignment for today, 902.2 Conservation of Energy Problem Set. It's not due until tomorrow. However, you are also going to be getting another problem set tomorrow that's due the next day. So just a heads up, I would not save a ton of it because you're going to be having to divide your time if you want to get started on 902.3 tomorrow as well. It won't be due tomorrow. There's not like you have two of them due the same night, but just they're going to be a little bit of overlap there because I want to make sure that you're using your time wisely. So you should have paper out. As you're solving these, you need to be able to write out your own equation for the math. So definitely take out some paper. You need a calculator. If you have questions as you're working, please let me know.